All right, hopefully you guys got some good shopping in this weekend. I spent way too much money, but we'll see. All right, here we go with section 15.3. So in section 15.3, we are not going to be just doing integrals or double integrals over rectangular or square regions that are bound by numbers. We're going to have to also do them over functions, all right? And so like different regions bound by certain functions. So you see right here, like this is bound by y equals 1 and y equals x. So that's a little bit different than what we've been doing. And so we're kind of trying to build up, and it's going to get a little bit more difficult as we go. Now, if somebody gave me a problem like this, I could just go ahead and try and do it, but I just want you to be able to understand the picture and why it's like this. And so let's go ahead and take a look. We'll draw a little picture of what's going on. So I have x and I have y. And so because dy is written first here, this is y equals 1 and y equals x. So y equals 1 goes across here. Y equals x goes there. They, of course, meet when x is equal to 1. And then over here I have x equal to 1, x equal to 2. So x equals to 1, x equals to 2 is this region right in here. So that is a little triangular region that we're doing here, there. So we're going to go ahead and do the integral, but just so you see the space and understand what you're doing. So this is basically kind of like your ceiling. This right here is acting as your ceiling, and it is hanging over that little space or under it or however it looks, but we are doing the volume of space between that surface that is up in the air and down to this on the xy plane. So here we go. So I'm integrating with respect to y first. I'm ignoring the x's. So that means that this becomes 2x squared. The y becomes negative 1 over negative 1, so negative there, plus 2y squared over 2, so just y squared. I have to evaluate this from y equals 1 to y equals x. Sometimes it's nice to put a y equals so you remember which letter you're doing. So I have dx left, and I still have my integral from 1 to 2. So this piece right here, I'm plugging in y equals x and y equals 1. So I have negative 2x squared. Y equals x means I'd have x to the negative 1 right here. So I'm going to put that down below, plus x squared. Minus when I plug in y equals 1, so that would be negative 2x squared. That would be a 1 there, plus 1 right here. All right, so if I clean this up a little bit, it comes out to, oh, wait a minute. Nope, sorry about that. Yeah, so it comes out to 3x squared minus 2x minus 1, and I'm doing the integral of that from 1 to 2. Now, like I said before, when we end up with a polynomial right there, we're just going to go ahead and pop that in the calculator, and the answer is 3. Okay? So whenever you come out with a polynomial, or whenever you can tell that you're going to come out with a polynomial, even if there's some other part to do, then that'll be fine. All right. This next one right here, we're going to draw this little region there. And so I have two trig functions. I have from y equals cosine to y equals sine. So if I draw that, y equals cosine x starts at 1 and goes down to negative 1 and back up, and that happens at 2 pi. This is at pi. Then if I have y equals sine of x, so y equals sine goes here, comes up and goes down to pi, and then back like that to there. We are doing this from pi equals 4 to 5 pi over 4. So it just so happens that pi over 4 is where they meet right here, and 5 pi over 4 is where they meet right there. So I'm really finding the space in between that. Now, if I look at this problem, what's happening here is I don't have a height. There is no function right there. Okay, so really what's happening here is I am really just doing the area between these two curves like you did last year. So last year this could have been presented as a problem like this. Hey, find the area between those two curves. So you would do the integral from where they met. And you would subtract, you do top minus bottom, right? So the top is a sine function and the cosine function is the bottom, and you do dx, which is what we're going to end up getting, what you'd end up getting here as well. So just know that if you want the area between two curves, you can integrate, and the basic height of your function, the surface that you're integrating over, is 1. Okay? So when I integrate this, I would end up with a y. So I'd have a single integral left. I'd have a y. I had to evaluate that from y equals cosine x to y equals sine x. I still have dx out here, and I'd still have, pi over 4 to 5 pi over 4. All right, so I plug in sine, plug in cosine, subtract, so I basically get sine x minus cosine x, integrating this from pi over 4 to 5 pi over 4. So when I evaluate this, I do my integral. Integral of sine would be negative cosine. Integral of cosine is sine. Evaluate this from pi over 4 to 5 pi over 4. And remember, pi over 4 gets you radical 2 over 2 and radical 2 over 2. So after you evaluate that, you get 2 radical 2. All right. So over here, I am doing the integral from y equals 0 to y equals x. So if I draw that region, y equals 0, of course, is right here. Y equals x going there. So from y equals 0 to y equals x, so that's going from here to here, so it's going up, down, right? And it's doing this from x equals 0 to 1, so from 0 to 1, so it's this region right here. And notice that when this starts off with y equals, we're going from, this is my top, and this is my bottom. Okay, so think of that just like you did over here. This was our top, and this is our bottom. Okay, so integral of cosine squared. Well, luckily I'm integrating with respect to y first because I could not integrate this with respect to x even if I wanted to right now. So that's why I have to do it with y first. So the integral with respect to y would just be y and then cosine of x squared. I would have to evaluate this from y equals 0 to y equals x. So when I get that, that creates an x out in front in place of the y, and then I get cosine of x squared. And then minus 0 times all that is just 0, so I still have to do the integral from 0 to 1 with dx. So great. So now I can do my u substitution. U equals x squared, du is 2x dx, so I can replace the x dx with a 1/2 du. So put a 1/2 integral cosine u du. Integral of cosine is sine, so I have sine, and then I put my u back, sorry about that, which would be x squared. Put the 1/2. And then from 0 to 1. So this ends up with 1/2 sine of 1 squared, which is 1. Because we plug in 0, you get 0. And so sine of 1, that's just some random value, get in your calculator. All right, so what we were doing and what you did last year, you were always going, when you wanted the area between two curves, you would do, top minus bottom. That's what you would think to yourself, and you would get this integral. So that's like I just explained to you in the last page. If you were to do the same thing with a double integral, you would just put those two functions here and here, and you would have a 1 right there. So what that gets you, if you want the area of a region, then you can do a double integral, and you put your functions here and here, and it basically ends up with the same thing you did before. So this leads us to what we are going to study first, are type 1 regions. Type 1 regions are when it is best to name your region or look at your region from top to bottom, right? Because the functions that you have contain the region from top to bottom, top minus bottom when you do the integral. Then type 2 was what we're going to finish off with, is when you do right to left. And remember, when you do right to left, when your functions limit your space from right to left, remember, you have to be solved for x. All right, so it's going to be a little bit weirder for us, but we'll get there. All right, so let's get back to this. So we are going to go ahead with our type 1 regions. These are going to be kind of easier for you because it's going to be kind of similar to what you're used to from last year for the most part. All right. So we're doing x plus 2y, double integral of that over that height basically, and we have to contain it above the region y equals 2x squared and y equals 1 plus x squared. So y equals 2x squared is a parabola, and y equals 1 plus x squared is a wider parabola touching at 1, because 2x squared got stretched a little bit. So those things meet up, and if you have to find out, 2x squared equals 1 plus x squared. So they meet at x squared equals 1, so x equals plus or minus 1. So I need to know that for my integrals here. All right, so you can see easily why this region is like a top-bottom region, because it's nice, this x squared plus 1 is the top. My 2x squared is my bottom. And so that's what I'm going to put on my first boundary for my integral. All right, so double integral. I'm going to do y equals 2x squared to y equals x squared plus 1. And you don't usually put the y equals, but I'm just trying to like make a point of it here. And then here I'm doing from x equals -1 to x equals 1. Now this region is symmetrical, so if you wanted to, you could just do from x equals 0 to x equals 1 and then double your answer. So if you wanted to do that, you could. Actually, no, don't, that is not true. But I thought I was being fancy there, because this region would not be necessarily symmetrical over this part right there. So forget that I said that. So anyway, I put my x plus 2y right here. I'm going to integrate with respect to y first and then with x on the end. So let's see, integral with respect to y, I have x squared over, and with respect to y, I don't know how I can say one thing and do another. That means that this would gain a y. Integral with respect to y of 2y would be 2y squared over 2, so just y squared. So I have to plug in 2x squared and x squared plus 1 into that. I still have my integral, I still have dx out here, but I need to work this out first. So I'm going to plug in for y. So I get x times x squared plus 1 plus x squared plus 1 squared minus, when I plug in 2x squared, so I get x times 2x squared, which would be 2x to the third, plus 2x squared squared, so it'd be 4x to the fourth. So you guys know how to square that out. You clean all this up, you actually end up with -3x to the fourth minus x to the third plus 2x squared plus x plus 1. Integral of that from -1 to 1 dx, and that's a polynomial, so you get 32 over 15 in your calculator. Okay. All right, and if you need to, I do have an app I could suggest to you. I think it costs a couple dollars or something like that, but it's a Wolfram Alpha, and it will do these integrals for you. Pretty nice. All right, so this next section. So this next problem, we're going to bound ourselves with y equals 1/2 x. So 1/2 x is a line with a slope of 1/2 going through the origin, and y equals radical x, so it comes across here. And where does 1/2 x equal the square root of x? Well, square both sides, I get 1/4 x squared equals x. I get 1/4 x squared minus x equals 0. Always try to factor out an x. So x equals 0 and x equals 4 are where they meet up. Okay? So they meet up right here at x equals 4 and 0 right there. So it says to go from 2 to 4, so that means I'm going to start at 2 to 4. And so you can see I have a top minus bottom situation, or top to bottom situation. All right, so when I do my double integral, I'm going to be doing dy first, because I'm going to go from y equals 1/2 x to y equals radical x. I'm integrating xy, and on the outside I'm going from x equals 2 to 4. All right, so integrating with respect to y, I get xy squared over 2. Do that from 1/2 x to radical x. So I plug in radical x, I get x times x up top, so it'd be x squared over 2. Minus, when I plug in 1/2 x, I will get x over 2 times y squared. I'm plugging in 1/2 x, so I get 1/4 x squared. So basically I'm integrating 1/2 x squared minus 1/8 x to the third. This is just a polynomial, 2 to 4, and dx. So we can go ahead and put that in our calculator. We get 11 over 6. Okay, so that is the volume of the region above this little shape right here, above that space, up to the place where this function kind of that surface hangs right there. All right, so this last little problem right here, we're going to set this up. I think we're just going to set this one up. We're not going to like do it all the way. So an artificial lake is bordered on one side by a straight dam, and then the shape of the lake surface is a region in the xy plane bordered by 2y equals 16 minus x squared and x plus 2y equals 4. So if I solve that for y, I get y equals 8 minus 1/2 x squared. So it's like a wider parabola, up, down, touches up here at 8, facing down, I meant to say, so a wider parabola, kind of facing down. All right, and the other one would be y equals negative 1/2 x plus 2. So if I graph that, it turns out that they meet up right there at 4. And you could graph these on Desmos. You don't even have to solve for y. Like you could literally in Desmos type this in, type that in, and get the picture that I just have right here. So that's pretty nice. But I do need to see where these things meet up. So they're both easily solvable for 2y. So then I would get 16 minus x squared equals 4 minus x. So I'm going to bring my x over to the right side. So I have x squared minus x minus 12. So when you factor that, you get x minus 4 and x plus 3. So these things meet up when x equals 4 and negative 3, which we already saw they meet up at 4. This other place is negative 3. So when I set up my integral, I would be doing the integral, and it's very easy to do top to bottom on this area. This side right here, this is the dam, the straight side that it's talking about. So it's easy to do top minus bottom, so I'm doing parabola on top and line on the bottom. So those are both y equals, so I'm going to have dy, and then parabola on top, solve for y, would be 8 minus 1/2 x squared. On the bottom, the equation, the line solve for y, would be negative 1/2 x plus 2. And we're going from the x values of negative 3 to 4. And we want the area, so that would be a 1 right here. Okay, so if you want to work that out, it comes out to 343 over 12, which equals 28.583 and on and on and on units squared. Okay, so that would be your solution there, but really it's just a lot of algebra. All right, so that was just solidifying the area of the region is when you integrate a double integral with 1. All right, so now type 2 regions. So type 2 regions is when you find yourself having to go right minus left. You can't do top minus bottom because the function is on top of itself in some way, and you'll see that in this first problem right here. All right, so if I look at this space right here, y equals x plus 1 is what's bounding me. I'm sorry, x minus 1, so it starts at negative 1, goes up 1 over 1, so there's that line. And this right here is a sideways parabola. If you were to graph that, it would cross over here at 3, and it comes across like sideways like this, and then it also comes down here. And again, you could put those right in Desmos, it would show you where they intersect. And so we're going to find where they intersect though. I got y squared equals 2x plus 6, so I'm going to do 2, plug in my x plus 6. X in this problem is y plus 1. So I'm using substitution there. So I got y squared minus 2y. Let's see, that'll be 8. So minus 8 equals 0. All right, so I got y minus 4 and y plus 2. So at y equals 4 and also negative 2 is where they meet up. All right, so that means that this is hitting when y is negative 2, and this is hitting when y equals 4. Okay, so that's going to be my outer side. So I can't do top to bottom in this problem because if I did top to bottom, you see how this would be subtracting itself. I would get nothing. I couldn't do it. All right. There is a way to do it, but it's a little bit harder. But anyway, I can't do top minus bottom because you end up meeting yourself. So that's why we have to do right minus left. So whenever you do right minus left, that means that you're going to do dx first. And that means that these equations here have to be solved for x. So you have to do x equals, so right minus left. Right is on the top up here. So the right side is the line. So the line solved for x would be y plus 1. And the left side is the parabola. So the parabola solved for x would be 1/2 y squared minus 3. So it's like if you turned your paper over, if you rotate it counterclockwise, 90 degrees, then you'd have top minus bottom if you wanted to think of it like that. But anyway, right minus left, this is the right, and this is the left. Right, and then I have to do an integral on the outside, but now that's y, and so those things meet up at the y values of -2 and 4. Right, and then I have xy right here. All right, so we're going to integrate with respect to x, so I'm going to get x squared over 2 times y. I have to evaluate this for my 1/2 y squared minus 3, and then y plus 1. So I'm plugging in y plus 1 right there. So y plus 1 squared over 2 times y minus plugging in 1/2 y squared minus 3 squared over 2 times y. Now this could be all worked out, and if it was, it would be a polynomial. So since we know it's going to turn into a polynomial, we're just going to be lazy and put it on our calculator. And then you would get 36. Okay. So you could do that as a type 1 region, but if you did, then you would have a lot of trouble. For instance, if you would have to break it up into 2 parts. You'd have to do this area right here by itself, and so you see I'm going from the bottom half to the top half, and then that is between -3 and -1. And then you would have to do the second region between the line and the parabola. So there's a line, there's parabola, and it lasts from -1 to 5, right? And actually that shouldn't be a 5, should it? It should be a 4. So fix that for me. Okay, and so that would just be a lot more work, and it would not be very pretty. All right, okay. So in these last problems here, we are going to just change the order of integration, because sometimes you have to be able to do that. All right, for instance, you don't have to write this down just yet, but like look here. If I tried to integrate this with respect to x first, I couldn't do it because there's no x sitting out here to act as my du for my x squared, so I couldn't do it. All right, this one over here, if I try to integrate with respect to y, I couldn't do it because there's no like y squared up here to act for my du, because the derivative of the y to the third would create a y squared, and I just couldn't do this. So sometimes you have to change the order of integration to be able to even do the problem. Other times you just do it because you don't want to do it the other way. All right, so here we go. So let's see. So I'm doing x equals y squared to x equals 4. That means that this is a right minus left right now, okay? So x equals y squared, that is a sideways parabola, and x equals 4 is here. So I'm doing right minus left. I'm going from y equals 0 to 2. So 0 to right here, which is 2. So that means it's doing right minus left of this piece right there. So instead, we're going to change it to a top and bottom. So if I'm changing it to top and bottom, that means I need dy and then dx. So top and bottom. My top part is this radical x function right there, because if I solve this equation, x equals y squared for y, it would be radical x, and that's the top half of it, so it's the positive radical x. So it would be radical x, and the bottom is 0. And I just put my function back. And now I do my x values. Well, this goes from 0 to 4. Okay. All right, with letter B. Letter B, if I was looking at this right now, it's y equals, so it is going from top to bottom. So this is now the top, and this is the bottom. So it's going up and down instead of right and left. So we're going to switch it to right and left. So y equals x is here, y equals 1 is right there. It is now going like this, but we're going to switch it the other way. We're going to do right minus left. It is going all the way until 1. All right, so that means that I have to go this direction. So that means I have to have dx. So I'm going from x equals 0 to this one right here. This is x equals y. So the right side of that is my x equals y, and my left side of it is the x equals 0. It is going from y equals 0 to y equals 1. And then you have e to the x over y. Okay? All right. Now, in letter C, like I said earlier, you couldn't integrate this way. So right now it is set up to do x equals. So it is set up to do, this is the left and this is the right. And we are going to change it to top and bottom. All right, so let's see what we got there. I don't like this green. So it's x equals y and x equals radical pi. So radical pi would be like 1 point something. So it'd be like over here, okay? So x equals radical pi, y equals x. All right, so it is going from right to left. So it's going like this right now. We're trying to change it to top to bottom. And it's going from 0, y equals 0 to pi right there. Okay, so we're changing it to top to bottom, so we're going up and down. So I'm going to have my top be y equals x, my bottom be y equals 0. I'm going to have my numbers be from 0 to radical pi. Oopsie. And this was radical pi, not just pi. And we got cosine of x squared, and then dx. So now you can actually do that problem. All right, so in this last example here, we are, let's see, y equals. So we are going from top to bottom right now, and we're going to change it to right to left. So we're going from y equals radical x, so y equals radical x looks like that, to y equals 2. So y equals 2. So we're doing top to bottom right now, and we're going to switch it the other way, and we're going from 0 to 4. So 4 is where they're meeting up right there. So we're going to switch it to go this way, so right minus left. So the right one is the radical x, but I got to solve it for x. So it's going to be y squared. The left side is this right here, so that's x equals 0. So that's my dx. And then dy, well, my y values go from 0 to 2, so that's that. And then I have 1 over y to the third plus 1. Okay? All right. So last problem here. I got couple pictures here of what's going on. We are not going to evaluate this. We're going to finish it up in class next time, but I just wanted you to see how to set this up. So we're going to make a double integral to find the volume of the solid bounded by the cylinder. And so you can see that cylinder has a radius 2. It's along the x-axis in these planes. X equals 2y, x equals 0, and z equals 0. So remember, z equals 0 is the xy plane. X equals 0 is the YZ plane. So it is cutting off, remember the X is the red, and this is your Y, and your Z is up here. All right, so it's cutting this off right here. It's cutting it off down below, so it's cutting it off there. And it does say the first octant, all right? So the first octant, you know, in 2 dimensions, you have quadrants, because when you have an XY plane, you have 1, 2, 3, 4 quadrants. Well, when you have 3 dimensions, you have octants. You have 8 octants. So it is like the positive, the first octant is the one where X, Y, and Z are all positive. So what we are doing right here is we are binding ourselves to this little section right here. So it's this little section right there. All right. So if I try to draw that in 2 dimensions to see the space that we're doing, I have the equation y equals 1/2 x. That's basically this line that's protruding, it's kind of hard to see, this line coming across here, the line of the plane, okay? So y equals 1/2 x, looks like that, okay? And it's being bound on top by the cylinder. Okay, and remember the cylinder is hitting the y-axis at 2 because that's the radius of it. All right, so we are going to do the double integral. My ceiling is my cylinder. So if I solve this thing for z, I get plus or minus square root of 4 minus y squared. So I'm using the positive part of that because it's in the first octant. So I have square root of 4 minus y squared. We are going to do, let's see, right here in this one, I cannot Since I'm doing this space like right in here, I want to do right minus left. So I want to have these things solve for x. So right minus left means I have dx first. And besides, I couldn't do the integral of this with respect to y right now. So good. All right, so it means I'm solved for x. So the right side of this is x equals 2y. The left side is x equals 0. And on the y-axis, I'm going from 0 to 2. Okay? All right, and so we're going to evaluate this in class later, but that's how you would set it up. And that is it. Bye-bye. Don't do this homework, by the way. You just